Okay, my name is Marius. Welcome. If you haven't seen the previous talks, I'm a PhD student here at the Berlin MoBI Brain-Body Imaging Lab. And I am going to talk in this session, the last hands-on session for today, about EEG group level analysis and especially repeated independent component clustering. So if we have a look at, I'm going to use the laser pointer. If we have a look at the current state, we already passed the preparation and the ICA and now the events. And here we are now at the clustering level. And tomorrow you'll have these more multi-dimensional analysis approaches. And this is basically still EEG only at this point, the IC clustering, and pretty much a classical approach with a few extra twists. So what do we have and what do you need if you want to follow along? So if you check the drive folder, there is the level 5 and level 7. 5 is a single subject EEG analysis. That's where the epoch files that Anna created are stored, and level 7 is the EEG study. That's the level, that's the storage folder for anything that is group level related, basically. And there is also this script. It's the hands-on clustering script here, pretty quick. And if you already have level 5 and 7 downloaded, the script doesn't take very long. So essentially, you can skip many steps because it's already pre-computed. But I just left it there so you know exactly what led to the final outcomes. Okay, so let's start with the hands-on session. If you want to, you can just load the data here. Again, you need to adapt the file path, and then you can just load all the data sets. This is still only the epoch data sets, both standing and walking. It's being loaded, and then the session afterwards, the section afterwards is actually creating the study. And this is these lines of code, 28 and subsequent. Basically, this is all something that you can also do in the GUI. I just this is nothing special here. Just so you can follow the script along. And the next part here, that is the component measures. This takes a little while. A few minutes only, and that basically creates the component measures for every component. It creates a bunch of measures that I will talk about in more details later, but you can start that now if you want to, and you're already in a few minutes then. So taking a step back, why do we do this clustering? And yeah, so what's behind that in the first place, right? So the core principle is that we want to do group level analysis. And if we are doing group level analysis on the sensor level, that's not much of an issue because everybody has the same sensor, assuming you didn't switch the EEG cap like out to a different model in between. So everybody has principally the same sensor. And if you want to do ERPs at, let's say, CZ, then you can do that for every participant. It's no problem. You get the same, you get a value for every participant. But this is not the case if you're going to the source level. So sources are similar, topographies may be similar, and some are really stable like eyes, yeah, some brain components are usually also looking pretty similar, but they are not identical. So if you want to compare, for example, this subject component activity with this subject's component activity, then you can see, okay, well, eyes are super similar. It's basically the same. But then it's already changing, right? So let's say we want to do component activity in a parietal cortex then it could be IC7 here in this case, could be IC14 there. It's just not entirely clear, judging from the topographies only. And that's an issue because we don't know which components we need to look at for every different participant. So that's the goal of the clustering, that we need to find sources that are comparable between participants so that we can do our group level statistics. In the end, ideally, we want to have one ERP for every participant, so then we can do our statistics on the P3 level, on the P3 mean amplitude, let's say from 250 to 350 milliseconds or something like that. So this is what we need the clustering for. Without the clustering, that's really difficult. And how does this work? As I said, we start with creating measures for every independent component that exists in the study, basically every IC of every participant. And these measures are, on the one hand, the dipole location. That's already been done in the ICA session before. So this is one of the reasons what we need the locations for. Probably the main reason if you want to do source level analysis. And in addition to that, we have other measures like the scalp topographies. You don't really need to create much here, but it's just stored in an additional vector for the clustering. And then other measures are also created, like the spectrum for every component, the spectrum here, and in this case, ERPs. You could also do ERSPs, so event-related spectral perturbations, if you want to go to the spectral analysis, but essentially it doesn't make a big difference. You have a functional measure, at least the spectrum is kind of a functional measure, and ERPs are definitely some sort of functional measure that you can also use for clustering. That's an issue, potentially. I'm coming to that. So now we have these measures. For every IC, we have this measure, and then we create a complete array of all these measures for every participant, every IC. And these ICs are then weighted, or these measures are then weighted. And in the end, there is a clustering being done. It's like a k-means approach, usually. And then you compare the data on this cluster. So you just plot the ERPs on a single cluster. That would be the core idea, if you, for example, are interested in parietal computation. So here we do have another hands-on session. And again, in the MoBI workshop, hands-on clustering script here, we can create the array. This takes a while, mostly because a lot of storage needs to be allocated and so on. So you can start that now, and it computes all these things. And here you add in the weights. The clustering weights in this case is the spectrum at 1, the ERP at 1, the scalp at 1, and the dipoles at 3. So the dipoles account in this case for half of the weights of the entire array. And in this case, you use the function MoBI precluster. You can do that in the GUI. The problem, if you use the GUI, you cannot do the repetitive clustering, which is going to be the next part. So the precluster, MoBI precluster, saves a few extra information parts in the study, and that's why you should use this if you want to do it. Essentially, it doesn't do anything different than the GUI. It just saves more information. So you definitely know that you can check it out later, even if you're not sure, for example, which weights you used a year later. You can definitely still know it if you check out the study file, if you use this function and not the GUI. So you can start that and let it run in the background. And in the meantime, I'm talking about this question: how do we choose the weights? If anyone knows, please let me know. There isn't really a rule for this. It's really difficult, and probably the biggest problem with the clustering that it's a lot of researcher degrees of freedom here. because you can basically choose the weights however you like them. And it's also a little bit intransparent to, yeah, I mean, you can change them. If you don't like the result, you just use a different result, a different weight set. There are some heuristics, obviously, that it's worth sticking to and also worth mentioning. But yeah, that's the biggest problem when using the clustering approach here. So first of all, probably it's a good idea to weigh the dipole location the highest. And that's because, I mean, that's the core issue, that we cannot compare the topographies alone. So that's why we do this dipole stuff in the first place. The problem with the dipoles only is that it's inaccurate in EEG. It's really not the best measure that we have in EEG. The locations that are fitted with like inaccurate algorithms in an ICA that is created based on a heuristical algorithm and so on. So we have a lot of fuzziness if we would only use the dipole locations as the only measure. That can be an issue because it might be inaccurate. So you should not ignore the topographies and the spectra. Probably you shouldn't weigh them super high. As I said, like they might be countering each other, which isn't great. But you can like give them some weight so that at least ICs that look very similar are probably taken together. And the spectra is also, the spectrum is kind of important in this case too, because it probably will separate brain components from other components rather nicely. In addition to that, you can use the functional measures like ERPs. I mean, if you're looking at EEG, these functional measures are the most powerful thing we have. That's the core thing why we do EEG, and they are comparably reliable. At least that's the basis of what we are assuming in our research. So yeah, you can use them too and fit them into your clustering array. But this is a little bit dangerous too, because I mean, it could be double dipping. So what is double dipping? If we use ERPs to select the clusters to compute our final ERP on, that's kind of circular, right? So it could be that we artificially increase our statistics by just fitting the cluster in a way that it increases our statistics, because because as I said, we use the same measure that we compute the statistics on to select the data. But there is a counter argument for this, and that is when you are doing this clustering with ERPs or other functional measures, you use the averaged ERP. So every IC has the averaged ERP over the conditions that they are. And in the end, the statistics that we compute, they are trying to find differences between the conditions. And this is, for example, the ERP of one IC, that's like IC 14, right? This is the average ERP right there. But if you look at the single trials, that's like the X is the time, and the Y axis here are the trials. That's like 700 trials throughout the entire experiment. If you look at the trials, you can visibly see that there must be different conditions. Like this is one condition, that's another condition, and here's one condition and another condition. Probably, I mean, we would have to see in the events to make sure here, but what we can see is that assuming that the conditions are that clearly separable, the average ERP won't be informative. So it probably won't inflate our statistics. Still, it is a dangerous path that you are treading. When you're doing that, you need to be aware of it, and you should not weigh it too highly. And then the last part, or that's the actual part, is that we do the clustering, and then you find the cluster near your region of interest. Let's say in this case, you are interested in the visual processing of a stimulus, which is here the right V1 area, and you have these clusters. In this case, it's only 4 ICs. Don't worry, this is correct because we only have 4 participants in this study. But if you have 20 participants, you should have more ICs in this cluster. And then you do the ERPs and do some statistics. In this case, I didn't do statistics because it's only 4 subjects. But you know the gist. From there on, it's normal ERP processing. It's just not the ERP on the sensor level, but instead it's the ERP on the source level. Okay, nice. Cool. So what's the issue here? We do have a problem. And that is that this k-means clustering is not stable. So this entire approach that I've been talking about is a classical approach that is being done when you're doing source analysis in EEG. But when you rerun the k-means clustering, you might get a totally different result. And this is kind of a common theme in EEG processing, as you've seen already with the rejection of channels, for example. Here we have another thing, which is basically the same issue, right? So it's difficult. We cannot just say we clustered with these weights and other people will probably get the same results. No, they might get the same results if you're lucky, but they might also not get the same results. So we have created a solution for this. And again, something repeated, in this case, repeated clustering. So what's happening here is that we create a cluster solution. And this cluster solution should have a good cluster in a region of interest. So this is hopefully a stable solution in the end, which gives you also a good solution for your computation. I'm going to discuss what good means in this case. So the approach here is, for every clustering solution, we cluster once, and then we select the cluster closest to the designated region of interest, in this case, entered into the function in M and I coordinates. And we do that, let's say, 1,000 times. So we have 1,000 clustering solutions, not 1,000 clusters, but 1,000 clustering solutions. And for every clustering solution, we have the closest cluster to our region of interest. And then we create quality measures for this region of interest cluster. And from that on, we create a multivariate quality data for all iterations combined. So we have, for every clustering solution, we have a set of like a vector of quality measures that is determined by the ROI cluster in that solution. And this quality measure is the number of subjects, the number of ICs per subject, the normalized spread of this cluster. So tighter clusters are usually better. Also about the subjects. So normally we want to have more subjects in our clusters. Ideally, we want to have every subject in our cluster, which is rarely the case, but the more, the better. And we don't want to have duplicate ICs per subject. So this is probably not great. We want to have this low. And the normalized spread too, we want to have tight clusters that are located close to our region of interest. And here we have the mean residual variance. I was talking about RV in my last session, which is basically saying keeping this value low is kind of assuring that you do get brainy clusters. So in this case, that's why if you're using this repeated clustering approach, you don't need to throw away ICs in your study. You just weigh this negatively, and the repeated clustering will find brainy clusters for you, even if you leave everything in your study. That's fine then. And then we have the distance from the region of interest that should be low, ideally. We want to have a ROI, like we want to have the cluster close to the area that we are interested in. And the last part here, that is an interesting addition. That's the Mahalanobis distance from the median of the multivariate distribution. So we have this multivariate distribution. And in addition to that, every cluster has a distance from the norm, which should be low. It should not be zero, because obviously if you only use this, if you only weigh this as the lowest and you ignore all the rest, you would get the most normal solution in your entire range of repetitions, right? But that's what this is for. We want to have a good solution. We don't want to tweak the statistics by adding ERPs in this case or something like that, but still we want to have solutions that are valuable for our study, right? We want to have many subjects. We want to have brainy ICs. We want to have close to our region of interest and so on. So that's why this should be there. This should be a thing that we look for, or like that we want to reduce. We don't want to be too far away from the average, but it shouldn't be the only thing, right? But it's definitely important to have this in, because otherwise you might get a total outlier. Even if all the rest is fine, it might be that you get a single outlier solution that's really problematic. So then we have this, and we create the weighted sum for every for every clustering solution. Let's say 1,000 solutions that we have there. For every solution, we create the weighted sum of the ROI cluster. So it's 6 values per solution, and we rank all iterations and choose the one with the highest score as the final solution, and that is then stored into your EEG study. And this is basically the whole thing. And I really want to emphasize that no functional measures are in this quality measure data, because if they were, that would be super problematic. But this is all blind measures. That's just ensuring that we get a decent neural data in our cluster, but it's not trying to already find data that suits our needs. Like, for example, if you want to have a higher signal-to-noise ratio or a higher peak in the ERP, and we would add this in the cluster right there, that would be absolutely problematic. So you cannot do that.